is B. Okay, that is the slope-intercept form. Is that okay? Everyone recall what the slope-intercept form is, right? Is that okay for this one? All right, slope-intercept form. Everyone, I hope you remember that. So and as we argue what is simple linear regression, simple means I only have one x. Okay, we focus on studying how x are related to y. Okay, and if you have another z, okay, then that usually we call multiple regression. Okay, but here we just have simple regression because only one, or one variable regression. And if you have another variable to explain, that would be multiple regression, right? Multiple regression may be something like this, right? You have z of z, so on and so forth, right? You can go on, you can continue to go, but we just go to the two variable. Okay. And some of you ask why you just focus on one, because when more than one, then the math will be very complicated. We require idea of some matrix idea, but that's why we don't go into detail, right? But now it's only two variable, things become easier. And as I said, we focus on linear. Linear means that this is like this, right? If non-linear, you have something like this: ABX plus CX squared, and so on and so forth, right? So if you do this, that's a bit quadratic, or cubic, depends on how many degree you want. But linear means it's a polynomial of degree 1, right? If you remember, you learn in high school, right? That's linear. Is that okay? Is that okay? Is there a question? No? Okay. So if no, then this is the goal, right? And the data what we have is bunch of x and y, right? So it will be something like this: x1 and y, right? In this like 20, 115, so on and so forth, right? Bunch of data, okay? And the goal is to find the line, okay? And we try to find the best line to fit this data point, and then we have to first define what is my best, okay? So that is the main thing, okay? So how do we define the line's best, right? So is this the best line, or you want a line that is like this, or you want a line that's like this, okay? Or the line is like this? Which one's the best, okay? How can you define what's the best, okay? And of course, best would mean that the line, the point should be as close as possible, right? The line, the point should not be too different, too much, okay? But how can you define what's the difference, right? So there are potentially different ways to define the distance, okay? And actually there are two important candidates, okay? Or actually more than three. Actually there are three natural candidates you can use, okay? First one, you can imagine that it is the vertical distance between the line and the point, which is the one we adopt, okay? This is the vertical distance, okay? And another candidate that you think in your mind would be natural is horizontal distance, right? And also there are something, oh, maybe I should use the pink one, right? So because I'm using the pink one, so this is, right? This is the line, right? And the other candidate would be, the final candidate can be this one, perpendicular distance. Okay, so with red, black, and blue, you can naturally think that will be a nice concept of distance between a line and point, right? And probably you would think which one would be the best. Okay, and in economics, okay, in regression, usually the one we adopt, the classical one is the red one. The reason is being that we use X to predict Y or to explain Y. So the red one is in fact predicting how good is our model, right? Because X, usually in experiment, we control X, right? We control the advertising as X and Y with sales, right? We can control X, okay? So that's why Y will be inadequacy of the model, okay? So this is one reason we use the blue, red one rather than blue one, right? Blue one is not very appropriate, right? So that's why we use the red one, okay? And some of you may think why the black one is also a reasonable one. Indeed, yes. And that is what sometimes we call lyso regression, another type of regression or rich regression. But that is commonly used, the black one commonly used in some machine learning or AI regression. But in economics, because we try to X predict Y, then this is the way you use, right? And in AI or big data, you don't know the direction. So that's why you want the best fit. Usually you would be using the black one will be sometimes used. But for regression, for our class, or actually for many other classes, they use the red one, the vertical distance, okay? So the meaning of finding the best line to fit this data point is to find the minimum vertical distance, okay? And as we learn from the vertical distance, right? And as we calculate the distance, we consider the idea we call square distance, like we calculate variance. We minimize the squared distance, right? Sum of square distance, rather than the absolute value, because of the math required to calculate is much simple than the absolute value. And of course, again, if you minimize the absolute value, that is also feasible. That we'll call median regression, but that is not our concern today. Okay, you can minimize you can minimize absolute value. Okay, that's also there, but we focus on the special case, squared vertical distance. Okay, let me repeat. We focus on the best line is the vertical square distance, and I explained to you why I focus on this, because all other consideration can also be done, but they have served different purpose. And as an introductory class, we focus on the vertical because of the accuracy is the vertical one, right? And why we want the square? Because square is easy to handle compared to absolute value. When you do absolute value, that's another type of regression, right? But we focus on the one we do is simple linear regression. Okay, so now if you have no problem, then we can directly go to the method that is called the least square method. And indeed, this method is pretty old. I think it is way before probability. This is something invented by one of the great mathematicians, Gauss. Okay, and he used this method to predict the return of a comet. So an asteroid that flying through the sky. I think that one get him very famous. Okay, so this is the line. Okay, right? Because you give the intercept and slope, right? This line, and this is the vertical distance, right? And what we care is sum of the square of the distance. Okay. Okay. And you just minus this for each point minus the A and B. Okay. Is that clear? What do you mean by that? So basically, let me draw it again in case you don't. Okay. So basically, just like this, you have X and Y. Okay. And your bunch of data point there. Okay. So this is X1, Y1, and say this is X2, Y2, okay? And the thing here is I want to have a line, okay? And this line will be Y hat equal to A plus BX, right? Oh, maybe this is not very good to be there. Okay. Okay. And this, right, is the D1. Why? Because this point will be x1 a plus bx1, right? Because according to this, right? So D1 is just we call this is y1 hat, right? Y1 hat minus y1, or we have a, how do we define? Sorry. Let me see. Oh, I just defined the other way around. So I define it as y1 minus y1 hat, right? So this is y1 minus a plus b x1. Okay, so that one will give you the d1, d2, right, and d3, so on and so forth, right? And you try to minimize this sum up to dn. Okay, and this each one, right? We know this y1, x1, the data, right? So the unknown is a and b, right? So that is what you try to do, is try to find a and b, which means that you try to find different line, right? Because different line means, say if you have another line, right? Then you have another type of d, right? So basically what you do is to find, so if you have another line, right? That will be another a, right? Another b, right? So you try to figure out different a, different b, right? Such that the distance is minimized. Is that clear? So you try to find a line, okay, such that this distance is minimized, and you minimize by looking at changing a and b, right? A is the slope, right? So a is the intercept, right? B the slope, right? If you took this is a, right? And the slope is b. And in this case, right? If here will be the a prime, right? The slope will be b prime, okay? So will be, you're trying to change different a prime and b prime, drawing line, minimize the vertical distance. Is that okay? You have some question? So note that all the green are the fixed thing, right? So just make sure the line is the minimized. Okay? And so you try to choose A and B to minimize this, right? So basically just looking at this line so that the distance, sum of distance is the red and the blue, the square the one is the minimum, okay? So that is minimize the vertical distance, okay? And we don't do the proof, although it's not difficult because this is a linear, so it's contrasting A and B, so it can be solved, okay? So you can see the proof in the slide, but I'm not going to prove anything in this class. So I just give you the final answer to this. So what is the best line? Okay, turn out to be the following. First, you will see if you rewrite this, okay, we write this guy. Let's write this guy. We write x bar is equal to a plus b. Okay, so first we have this one. What does that mean? It means that the line will pass through the center of data, right? Why I call center of data? Because there is a bunch of x here, right? So you can calculate x bar as x1 plus up to xn over n, right? So this is middle of x, okay? And you have the same for middle of y, mean of y, right? And right. So the first thing you said is, if I want the line that is best fitting the curve, it must pass through the center of data, which is x bar, y bar. Okay. So Why the case? I mean, that can be to prove it, but it will definitely pass through the center of data. Is that okay? So there's nothing, I mean, of course, you would not be able to understand why because you don't go the proof, but I guess this is pretty reasonable, right? Because it's going to be the best point, then it's interesting property will be you're passing through the center of the data. Okay. And the second one probably would not be surprised you as well. B is also a very something that you would not be too much surprised. Turn out to be a fraction where the numerator, okay, is something familiar, which is the covariance part. If you ignore the denominator, right? This is covariance over n, right? And if you look at the denominator, right, which is just the variance of x over n, right? So basically it's covariance over variance. All right. So, and if you have, okay. One more thing here, right? Oh, sorry. I think it's a bad notation. I guess it's, I should say, not multiply, right? Okay, they cancel out. Right? So, and you can see that this covariance, right, is trying to tell you how x and y are related, right? Remember covariance, how x and y are related, right? And what it said here is it's just related to covariance because covariance how x and y are linear related, right? So that's why having the covariance is very natural. Okay. And the reason why you see the variance at the denominator, the reason is the formula is right. It's like this, right? It's a times bx, right? So that means that if you try to double the scale of x, right, you should more or less remain the same slope, right? Or you just reduce it, right? So suppose you can imagine the idea is like this, right? Suppose I have this x and y are a bunch of line, okay? And I just have this line there, right? But now I say double the data, right? That means that they will be a little bit longer there, right? So you should expect the similar line would happen, right? Passing through the same intercept, right? But the slope it just increase, right? All right. So you should be expecting that you should divide the by variance so that to make sure that everything is all right. Okay. And do I have the graph to show? Okay, this is a good one. So if you multiply the x to double, okay, and your b will get half. Why? Okay, look at the formula here. If you double this guy, right, everything you multiply by 2 times, right? That the numerator will be doubled by 2, right? And your denominator will double by 4, right? So the whole b is by half, okay? But if you have, say, a plus bx, right? So if you double this guy, you halve this guy, then you get back the original equation, right? So x, you double it, doesn't really make a difference. Okay, so that's why you have this equation. And the next is because the data passing through the center, okay? So if you change the data by subtracting the mean, you will still have the same slope, okay? The reason is like this diagram. I think that's easiest to look at the diagram here. So because in this case, right, the data is passing through the center, okay? So if you subtract the data, this means that you basically move your scale, this origin, you move it to here, okay? So you should basically draw the same graph, but just A becomes 0, right? Because you're passing through the center, okay? So now let me go through one line by line. So first is you pass the data, set of data that we have said already. Second is if you have positive covariance, you should have positive line, right? That is very natural as expect, right? Because covariance, looking at how they're related. If x and y are negatively, if you have a 0 covariance, that you have a 0 line, okay? And it means that in case of covariance, right, this regression model has no meaning, has no predictive power, because you don't use any x to help us to predict y, right? So regardless of x, your model is always y bar, right? So that is something that x actually cannot use for any helpful thing, right? Just like how many years you spend in school has no impact on earning, so it doesn't really matter to go to school or not, right? Or the advertising expense has no impact on sales, so you rather not invest any money on the advertisement, okay? And in this case, is the covariance negative, right? You should expect the slope of your line will be negative, okay? So that's why covariance is a very good reason should be correlated with your slope B, right? And here we can see why increase in variance of x would make your slope decrease, right? Because remember, B is, right? B is given by covariance xy over variance of x, right? So we should expect variance x goes up, B would go down, okay? So you try to look at the red one as original one, okay? The red one is original line. Okay, original line is like this, okay? And now your variance increase, okay? Variance increase means what? Only increase variance of x, y keep unchanged. So it means that everything that look at the center of x, okay, is move away in this direction, right? Just move a little bit away. Okay, here I move the same. Okay, so here I maintain the variance of y is the same, right? The y is the same because vertical distance is the same, right? For each one, right? Same. Okay. But I have a variance of x, okay, that goes up. Okay, in that case, you can see the line rotate, right? And rotate means the slope increase. Okay, so you can see the same drawing when you have negative one, just the same as like this and this, right? The same thing. So that is explain why when you increase the variance, that is going to increase your B, right? Because increased variance means it's going to rotate the line, right? And when the variance, actually, you can see when the variance go to very large, right? Go to infinity, go to very large, okay? That means that log x6 lie very far away, okay? Then the best line will be very close to like this, right? The more, right? And eventually it will become a flat line, okay? So that's why the slope is related to variance of x, right? How variability of x, right? The more the x, the further, then is where the line will become much stretched out, and eventually it become a horizontal line. Okay, is that clear why we have variance x increase would make the line fatter? Is that okay? Is there any question? Okay. Of course, I just trying to give you some idea why this is true. Okay. And here, as I said, if you try to double the x, okay, it moves further, right? And if you don't change y, but just multiply x 2 times, actually the slope actually will become half. Right? So that is the main idea here. Okay. I think I explained this graph already. And here, if you sorry, the typo here. A, okay, this is A here. If you y goes up by 1, A go by 1, right? How you get this result is coming from the fact that A is y bar minus bx bar, right? So if every y go by 1 means y bar go by 1 as well. Is that clear? Because A is y bar minus this guy, right? You go by 1, you only change the A. There's no change in the covariance. Okay. So that is the main thing. Try to see why we have this. Okay. So now I guess it is good to see how this thing to practice. Okay. So we have this data. Okay. Xi, yi have 5 numbers. So how can we solve the line? Okay, find the line that best fit the data. And actually we learn how to work it out. Okay. And this comes from, okay, first it's a slope. Okay. The slope can be coming from, you can do the direct calculation, okay, which I show later, or you can do the covariance over variance, right? So that is the goal. Okay. So let's see how we can do it, and I'll show you how to do it in Excel quickly. Okay. So for this one, we have a bunch of data y and x, right? And you can easily see that mean of x is 3, right? Because at the middle. And less easily you can see mean of y is 6, but just adding all up divided by 6. Okay. So this is usually how you can do in the spreadsheet, right? So you just subtract each number by the mean, right? -3 here, -3 here. So you get all this number x. Okay. And you can also subtract all the number by 6. Okay, you also get this guy. Okay. And then you cross multiply these two, you get you this column will give you this column, right? That's multiply, right? -2 is 4, -1 is -1, 0 and 0 is 0, right? 1 -2, -2, 2 and 3 and 6, right? And then lastly, you have a square of this guy, right? It's 4, 1, 0 is 0, 1 is 1, 2, 2, 2 to 4, right? And you add up this column, right? This is 3, still 3, and 1, that's 6, that's 7, right? And add up all this column is 10. So that's why it's 0.7. And once you know this is 0.7, you just basically put in the slope, right? 0.7 times 3, right? So this is 3.9. Okay. So before the break, let me show you the Excel. You can do it quickly. Okay. So it's very fast. Okay. Although you may want to calculate that, but Excel will able you to calculate much faster. Okay. So let me show you quickly how you can do in Excel. Y and X. We have 4, 7, 6, 4, 9. Okay. And 1, 2, 3, 4, 5. Okay. So this is the data. Okay. And slope can be coming from variance over covariance over variance. So that's why I think covariance XY. Okay. And we're fifthing variance of X. Okay. We can also do the mean of X, X bar and Y bar. Okay. X bar is just average of X. Right. So that's something simple. Okay. And we also have variance average of Y. Okay. And we have variance, covariance variance. You may want to ask whether I want to use the population one or the sample version. Doesn't really matter. As long as you do it consistently, that's fine. So let me use the sample version. Doesn't really matter. Covariance P. So I use the sample version. S. Okay. Covariance Y and covariance X. Okay. And I can have the variance of X. Okay. So I have all the information I want. So I can have B and A. The slope will be just covariance over variance. All right. And A will be just, remember the formula. Okay. Just this is just covariance over variance. Okay. And A will be just Y bar minus BX bar. Okay. So will be simply Y bar minus D6, okay, times X bar. So 3.9. So that is how you get this one. Okay. So, but that being said, Excel have a very smart function. You don't need to do all this. There's a function called slope intercept. Okay. So we can do A and B immediately. So that is called slope and intercept. Slope, just slope. Very simple, just a slope. Okay. And then you tell them what are the Y, what are the X. So this is the Y and this is the X. Okay, so you can see the answer there. The intercept is just the same. Intercept Y, that's X. You're done. So you can see, okay, I hope, how you can do it quickly. In Excel, you draw a best fit line, okay? So you give a model, okay? And this is the line that you will give, okay? And you may ask how it's useful because this is a line. This become a model because we don't need the data. The data give us the model, and this model will be our prediction, right? Because if this is data, maybe X the sales, so X advertising expense, Y is the sales, right? And the question is, the boss asks you, what happens if we spend 2.5 million, right, in the expertise expense? Then what would be the sales? Then you would do it just 3.9 plus 0.7 times 2.5, right? If the boss asks you, if I spend $2.5 million, what's the sales? Then this is the result. Okay. So I guess I have a break here. I'll go around to similar question. That's a 10 minutes break. So this is a regression.
Ông tin mapping của cả.
I guess we can resume. So you can see here basically nothing with the probability, right? Because everything is just math. Okay. And now we want to see some probability here, right? Because this is nothing if you ever learn high school, any high school math would do, right? Because and we just minimize the distance. There's nothing to talk about probability, right? And the goal is trying to say, if we have some probability here, do we still do the same thing, okay? So I will make precise what I meant by here, but here we are going to, what we're going to do is try to give the meaning to the model, even we talk about probability, okay? So we will have something to go now, okay? So we skip the proof. So the main idea is what we call the, later we'll prove what we call the Gauss Markov theorem. Okay, Gauss is actually the Gauss that the well-known mathematician. Okay. So what is said is the following. Okay, so here we try to what we call the classical four assumption here, and we try to make this four assumption to this model, and that means that this model become a probability model. Okay, a model. If this model works, and this is the model that generated data, then we are trying to estimate the model. Okay. So what do we mean by that is, let's go one by one. First one is we have y and x, right? Remember? Okay. And how y as x are related in the population, okay, is related linearly, okay, by some unknown population parameter alpha and beta, okay? If you are A, say this is education, say suppose, okay? It's income, okay? What is said is, if you get one more year of education, you get beta more income, okay? And people have no education, on average, who have alpha income, right? And this model is probabilistic. It's only coming from this element here, okay? This element we call error is the element that create probability, okay? X and Y are related in a linearly, but there's a probability error term, epsilon I. This epsilon I is going to make the model different, right? Why we need that? Because people with same education have different income. How can you explain that? The explanation is coming from the epsilon I, okay? Everyone would have some thing that is random. And how do you think what's the random there? The random can become from the things that we don't model. For example, what affect income, but not education, maybe your IQ, how beautiful you are, how handsome you are, what's your EQ, so on and so forth, right? And things that we do not model is the epsilon I, right? So that's why I call error, or sometimes called random term, that is the term here. Is that clear? So the first assumption say y and x generate through linear manner, although we don't know alpha and beta which we will estimate, but alpha and beta are the how x and y are related, okay? But how they relate is not clean because there's unknown random, okay, epsilon, okay? This is the first assumption. The second assumption, which sometimes people are not very happy, but that's what we have, is x are not random. That means that xi are usually coming from experiment, okay? And that is usually find in science or your marketing department. You try to see how they're decided, right? It's a control, right? That's education, you decide, right? Kind of. In those cases, then you can, this is satisfied, okay? And the next one, which is more or less trivial, okay? The first one is trivial, okay? Which said this random term have mean is 0, okay? This is trivial because we always alpha there, right? Alpha will be absorbing that, okay, if it's not 0. So this is rather nothing very difficult, okay? But one thing that is going to be crucial is this one, right? This is going to be same as what we call ANOVA, right? ANOVA, or the variance of t-test, right? We assume each outcome have the same variance, right? There's no difference in the variance of each observation, right? There's n different observation, okay? So here, this is important, okay? And this is a very important assumption there. And if you learn advanced class, you will relax this assumption. If you learn 2021, we can relax this assumption. It's not a problem, okay? This is easy to deal with, but often this is a source of error. And this is how you tackle this in different scenario will be the concern of different chapters, okay? But this is not our problem, okay? The last assumption is saying that random error, which something you didn't measure, are uncorrelated with each other, okay? So this is 0, okay? And this is the t-test, we have the independence, right? Each observation is independent, okay? Same as the independent assumption when you talk about the t-test. It's not pair, but independent. And this is important because if you don't have this, actually, when you talk about time series data, you don't have this problem. You don't have this will violate, right? And when you talk about stock market, you have trend, right? Then that's violate, right? If say inflation, usually it's violate, right? Because if you have inflation, this period is high, next period tend to be high as well, right? Or stock market, today's price goes up, tomorrow price tend to go up, right? If that is true, then the fourth assumption is violate, right? And if you really want to see how to solve this, this actually will be another advanced class talk about time series analysis. And that is not the concern of us because if you really study those. So that means that everything actually in this model can be relaxed, okay? And if you relax them, will be a huge class. You focus on one class, okay? Studying how, number 4, right? If they're related, it's a time series analysis. That will be a class by itself, okay? And almost everything, if you try to make it more general, it becomes a whole class by itself. So, but we focus on this classical assumption. First, this is the right model, okay? They are related linearly. Second, X are non-random. Third, this is the error term have mean 0 and variance are same, and they are uncorrelated with each other, okay? And all of them can be relaxed, but that is what we have, okay? So what is we make this 4 assumption somewhat strong. So what's the gain of these assumptions, okay? The gain of this assumption is the following, okay? Is we calculate A and B, right? Remember, B is covariance over variance. A is the y bar minus bx bar, that one, this A and B there. If we impose this assumption of 4 assumptions there, Gauss Markov theorem, which we don't prove, okay? It's a long proof there, but what we're saying that A and B are unbiased estimator of alpha and beta. Okay? So it means that if we think the data generated according to what we propose, the method we do minimize the distance, okay, whatever distance, is indeed trying to guess the right line. Okay? And not only the unbiased, the second thing is also important is they're efficient. Right? Which means that these estimators are hitting the target with less error. Right? And of course, efficient is have some qualification, only focus on other estimator, also linear in Y. Okay. So of course, this is very technical, but you can just, in your mind, you just need to remember they are unbiased and they are accurate. Okay. Right. In most, and recent research, actually just last year, they saw actually you don't need this guy as well. So the modern version means that they're very good, very good. So that's something you can remember. So if you don't want to remember anything, you can just say the Gauss Markov theorem tells you the minimize the vertical distance is very good. Okay, that's it. If you want to be more detailed how good they are, means they're unbiased and they're efficient. Okay, is that okay? So I guess now we can give you the interpretation, right? Now with the line, right? So this line, there are two things we remember. First is in mechanically minimize the distance, right? Sum of the square distance, that's the least square method. And second, according to Gauss Markov theorem, if you believe the data generate between X and Y are a linear line, okay? And this is the best line we can come up with, which is the unbiased and efficient, okay? And that is the line, okay? So we have the best fit line here. So can we have A and B. So what is the interpretation of A and B, okay? So we have the two. So what is A? A will be what is your expected Y if X is 0, okay? So what does that mean? Let me repeat. The analog is this is education and this income. What does that mean? A means that if you don't go to school, what's the salary of A, right? This is the raw labor salary. Maybe this minimum wage, right? A would be the minimum wage or the wage that you get if you go to work, go to do the job without, we don't need any education, right? Raw labor wage. Okay? That's A, okay? Do look at this interpretation, okay? Will be meaningful or will be useful if your data have value that of for X close to 0, right? If otherwise, that is meaningless. What do you mean by that? What I mean is it's the following, okay? So you have bunch of data, okay? Bunch of data here. Okay? I don't know. Then you try to draw a line here, right? And this is your A. Right? This is X, this is Y, right? A will be your expected value if X is 0, right? And this will be meaningful or useful if there are value next to X. Otherwise, actually, the interpretation is not very useful. Right? Because of the fact that actually there's maybe no meaning of X is 0. Right? Why is the case? Suppose the following. X is number of number of hours of sleeping. Okay. Okay, maybe I draw another one. So number of hours sleep. Okay. And this is GPA or exam score. So suppose in our class like this. Okay. This is maybe GPA 4 here. Okay. So what's the best fit line here? Okay. So it means if you don't sleep, you get GPA of 5, which first, GPA 5 doesn't exist. Second, no one sleeping 0 hours and then you die, right? Only dead men sleep 0 hours, okay? So the meaning of 0, you have to be careful, okay? First is no one is going to sleep for 0 hours, right? No one's going, this is not feasible. This is not going to feasible, right? If you're here, then basically it's like this, right? You die, right? And second, this more than 4 is also not meaningful, right? Third is there's no data here, okay? So join the line, extrapolate too long will not be very useful. So the only meaningful, you will say only belong to this area, right? As long as the data is within this region, this is only meaningful thing, okay? So the interpretation of A, to be careful, only is meaningful if there's data around there, right? The further away, actually later you will see, the further away from that line, you would put very little confidence on those, okay? And later you will see this idea actually we will, at the very end of the slide, we will talk about when we do prediction, we will have a very large confidence interval, okay? The further away from the mean of X, the interval will be much larger, okay? Which we'll talk about at the end, so don't worry. This interpretation we will see at the end, okay? I mean, if you can't wait, you can look at the very last page of slide, you can see that, okay? But unless we wait until the end. Is that clear? Why the A is important? Is that clear? How interpret A? Okay, A is only meaningful when where X is nearby the 0. Otherwise, you don't want to put too much weight on it. Okay. The next thing is I want to say is about the B, but B, I think this is the best thing of this model. Okay, because B is the key idea because you want to look at how X and Y are related, right? And B tells you what? If you increase X by 1, Y will be increased expected by B, right? That's mean of slope. Let me repeat. If you increase X by 1, Y will be increased by B. Of course, if you decrease X by 1 and then there's, okay? And do note that, okay, by simply running a regression doesn't entitle you to say increase X will increase Y. It's not causality here, okay? To establish causality, you need more evidence, okay? Because you can just run Y over X, X over Y, so you cannot say which one causes which one, okay? Okay, didn't say anything about that thing, okay? But we just say association, right? Say, even if I talk about education and income, okay? Why is not causation, right? If you ask the question, you have education here, you have income here, right? And you say, okay, education go first, income go second, right? The temporal thing, right? If you have more education, more income, right? And that doesn't mean X cause Y. Even you have the time dimension, okay? One go first, one go after. Actually, doesn't tell you any about cause and effect. The reason is a simple idea why this is not going to be a cause and effect, because you may imagine IQ is affecting both, right? People with high IQ would have more education in general, right? Because they find education easier. And people with high IQ tend to earn more because they can do better, right? IQ or EQ can be also EQ as well, because we don't want to be too narrow, right? Can be EQ or AQ or whatever Q you want, right? Because many Q these days, okay? And so just running regression is very difficult to say how they're related, okay? Unless you can control X. You are the experiment, right? You randomize over X, right? And then you can say, that's how science works, right? And if you are just able to make guy number 1 study a master, guy number 2 just do the kindergarten, guy number 3 primary school, guy number 4 secondary school. If you can do this, which is not possible, but if suppose you can do this, you're a dictator, you can do that, then you can figure that out, okay? But if you don't, then you don't, okay? Unless you have full control, okay? And do note that what we try to explain, okay, is not about the way we describe, it's about the variation of Y associated variation of X, okay? Just like how the thing we try to explain is, look at the graph, it will be easier to explain, to say, okay? The main thing we try to explain is like this, okay? We're trying to say, if X is above here, right? And Y is above this guy, okay? So we're basically talking about how the X deviate from the mean and how Y deviate from the mean, okay? Just to go back to the interpretation, right? Because you can imagine, if B is 0, okay? If X is completely useless, okay? If you don't use X, what is the guess of Y, okay? If education has no meaning to income, how to predict a guy's income? Put a random guy there. You will use what? Y bar, right? The average income is the best predictor. If you don't know, you should randomly pick up a guy on the street, right? But if you know his income, right, what you guess will become a, right? So before you guess is Y bar, right? You put a random guy there, Y bar. But now what you're trying to do is you try to explain this difference, right? And how do you explain this difference? It's trying to look at how X is different from X bar, right? Because if you run the regression, this is what you get, right? This will be the B of X minus X bar, right? So that is, if you minus this, the slope will be A will be 0, right? Because that is the line you draw, okay? So the main idea here is, okay, just for simplicity, just saying that you're talking about how variation of Y associated with X, okay? Because if all the X have no variance, okay, if all the X has just 1 point, your model will be useless, right? Because if you imagine, if your data is like this, okay, if data is like this, right? There's a Y. So your model is pretty useless because there's no variance of X. Then you cannot, what it's going to explain, right? So basically you are exploiting the variance of X to explain the variance of Y. Okay? How X deviate from his mean, then you give you idea how Y is changing from its own mean, right? Is that clear? Is that clear what I'm saying? Because if there's no variance on X, then your model is useless, right? So that's why you say how the X changes, how vary from the mean, and then that will tell us how Y vary from its own mean. Okay. Of course, these are more fine interpretation, right? But you just need to know regression as a take away is just the best fit line, right? And A is the intercept, B the slope, right? And this more finer interpretation, okay? And don't worry, this will be the emphasis of probably the advanced class, right? But we are focusing on the computational side, right? So you just don't need to worry too much about how we interpret, but okay. Okay. So what we are going to do, once we estimate alpha, so A and B, right, which is estimate of alpha and beta, what we want to do is we want to do two things. Hypothesis testing, right? We want to do estimation, right? With A and B, right? We want to see if these A and B are different from 0 or not, right? We want to see if the slope is actually the slope. It's actually 0 or not, right? We want to see B is 0 or not. We want to see A is 0 or not, right? This is hypothesis testing, right? The second would be we want to say this is just a point estimate, right? A and B. We want to know 95% confidence level. Okay. Okay. That will be the two goals there. Okay. And the third goal will be, which we'll cover next class, will be we are predicting the Y, right? So we want to have a also construct a confidence level for prediction. Okay, that will be the end goal of this regression. Okay, so now you know how to estimate. So we spend some time on how to do the hypothesis testing. Okay, is that clear what we are doing? Okay, you are done with the estimation, right? The point estimate, we come to the point estimate, right? We told you the estimate you got is unbiased and efficient. So what next is same as what we do in our class, progress, we do hypothesis testing and estimation, okay? How can you do that, okay? First, there's something in the model, we have an estimate, right? If you try to look back our model, okay? We have alpha and beta, okay? There's something that is not being estimated is the sigma square, right? Everything is there. We have alpha and beta. Sigma square is something we didn't estimate, right? So the first thing we want to study is how to estimate sigma square. Why we need that? Okay. Later we will see, because this is a random, right? If it's a random, what you get is A and B, right? The A and B will also be a random variable. Okay, let me repeat. Depends on what data you draw, this epsilon, big and small, you will decide what's A and B you have. Right? So A and B are random variable. Okay? And that's why you will do hypothesis testing, right? So that's the reason. That's why we call unbiased estimator, right? Because A and B are random variable. So how can we estimate the epsilon, so sigma? Remember, this is the error, right? And we say the variance of epsilon I is sigma, right? This is the assumption that we run the regression, right? So how can we estimate sigma square? the way we do it is just very simple. Just do the sample counterpart, right? So we just replace A by alpha, beta by B, okay? We do this part, okay? And we can find the sample variance of this guy, okay? That's what we're doing. You will probably ask why I don't have this guy. Why don't I write that, right? Because this is the variance. Okay. The reason is the way we write this guy is, sorry, you don't have I. This guy is always 0. That's why you just square. Okay. I don't think we prove it here, but the average error will be 0 because the way you fit the line, it can be proved, but I'm not going to prove it. But that's why you have a square there. And the reason why n minus 2, okay, I'm not going to prove it, but the idea is very simple because you estimate 2 parameters. You estimate alpha and beta there, right? As I said, if you try to estimate variance, the number of the thing you estimate, you have to subtract from the denominator. Here, you estimate 2 things, alpha and beta, so you minus 2. Is that clear? In the standard case, you just estimate the x bar, so that's why minus 1. In this model, you minus 2. You can easily imagine that in this case, if you have only one variable, you have x like more x, y, z, a, b, c, you have many more explanatory variable, then you minus how many of them, right? In this case, I only have 1, so that's why minus 2. Okay. So is that okay? So this is what we're doing, is trying to use this guy as a way to estimate sigma square. Okay, S square is trying to estimate sigma square. Okay, because this is what you're trying to do. Maybe I just going to give you a diagram to see why this is the case. Okay, hopefully this will be useful. So this is x and y. Okay, and so this is the y times alpha plus beta x. Okay, so in ideal world, x and y are written in this way. Okay, but if you try to collect data, okay, your data is polluted by error term, right? Maybe you have data here, supposed to be here, but what you get may be this guy. Okay, the difference is epsilon, right? Suppose this is x1, okay, and you have epsilon 1 here. So what you get is y1 here, right? Okay, so because this one is, this point will be x1 alpha plus beta x1, right? But actually what you get in the real world, right, is this point will be x1 alpha plus beta x1 plus epsilon. Oh, sorry, I used the epsilon, right? Will be the epsilon 1 here. Okay, this epsilon 1. Okay, so this is how the data being generated, right? And this epsilon, right, has sigma square, right? So each time you draw can be very different, right? But this is the variance. Okay, and we remember when you collect data, okay, maybe the data like this, right? You just data like this, right? And you may end up in line like this, okay? So you may end up like in this, right? So you end up your answer, this is your A, and this is your B, right? So this is the one case. You have another case, right? Depends on what data you draw on, right? This is become a Y hat A and B X, right? So this is a one possible line there, right? And how you estimate sigma, right? The way you do is you subtract this from a line that's become E, right? There's a bunch of E's, right? Bunch of E's here, okay? And this E1, E2, say E3, E4, and so on and so forth, right? And you calculate the standard deviation of this line. This gives you the S, right? This gives you the S. Right? S squared will be just sum of EI squared, right? Maybe I just don't use it, maybe E1 square, E2 square, right? Up to En square over n minus 2, right? So this will help us to estimate the sigma. Is that clear? Because the underlying error, right, come from epsilon, and then you try to use the same thing to try to guess the sigma. Is that okay? Is that clear what we are doing? Is that okay? Or any question? It's not that easy to visualize. The red one is something you don't observe, okay? It's hypothetical there. You never know it, okay? And what we want to guess is the variance of each error term epsilon, right? So how can we guess that? We do the same thing on the regression. The orange is something we observe. And we try to look at the distance between the line and the data point and calculate the variance. That is how you do it. Is that clear? Any question? Because this is something not easy to see. I remember when I learned it, it's not that easy, for sure. I mean, the formula is easy to remember, easy to run the regression, but to understand what is behind require a lot of effort, mental effort, okay? But if you just want to apply to know it, that's simple, okay? Because that's the formula, you just plug in there, done, okay? The difficult part lies on whether to understand what is going on, okay? Because the formula, it's just everyone can run it, okay? So anyway, I hope I give you some idea how this can be understood. Is that okay? Any question? Because the estimation of this S, okay, can tell us how to test whether A is 0 or not, right? Because orange is a one line, right? And in other scenario, we call it other data, you may end up here, right? Maybe data is like this, okay? And you end up with this line, right? This will actually give you another one, A prime, B prime of X, right? So what you want to do next will be saying whether A is different from 0, sorry, alpha from 0 or beta from 0. Okay? Is that a question? I hope that is clear. Okay. Now, if there's no question, then let's talk the first test. That would be no question. The first test. Okay. But before we do that, let's go to the example, how you calculate the S. Okay. So as I said, this is your X and this is your Y. Okay. And remember how you calculate this one. And because this guy is what? Is A plus BXI, right? And A is, I forgot. A is what? A is 3.9 and B is 0.7, okay? A is 3.5, 3.9, B is 0.7, right? So how can you get 4.6? Is 1 times 0.7 plus 3.9, that's 4.6, right? This is come from 3.9 plus 0.7 times 0.1, right? If you get 5.3 will be, I'll get it, 2 plus, sorry, is 3.9 plus 0.7 times 2. Sorry, that's, okay. Is that clear how you get the number of y hat, right? Y hat is the line, right? It's a line. Is that clear? What's it? Is that clear what's y hat? Right? Y hat is just your bunch of data here, right? And this y hat, the estimated one. Okay. And the e's are coming from the vertical distance, right? So that's why E is just simply yi minus yi hat. Okay, so that's why y negative 0.6 comes from 4 minus 4.6, right? So now how you get the S, okay? How you estimate the sigma square is the square of each term add together, right? That's the formula. And divided by n minus 2, okay? That gives you 4.367, okay? And you take the square root, okay? That's called S, okay? And this S, I forgot to mention the last line. This is what we call the standard error of estimate. If you go back to the last line, there's an important name to this one. It's called standard error estimate. Okay? It's the square root of that one. Okay? And as I promised you, I mean, average of E is actually 0, right? Because the sum of them is 0. Okay? So, but that should not be surprising. Is that okay? This is how you can estimate sigma square. Okay? And is there any question? Any question? And let me, okay, this can be shown, okay? We don't do it, but if you do tedious calculation, turn out to be, this is exactly what we want, okay? The expected S is sigma square. We're not proving it, okay? It's very tedious to prove it, okay? And I'm not going to show it in my slide, okay? And what I'm going to do, I'm not going any further, but I'm going to give you a structure of what we're doing, okay? Because that is good to preview what we're doing, okay? So what we're trying to do is trying to see, okay, how to interpret the A, okay? And same as before, if you don't make any assumption on the epsilon, we cannot go further. So if you allow epsilon follow the bell curve, okay, if you allow the epsilon as a bell curve, turn out A is also a bell curve. Okay, so it means the following. It means that if the error you have is like a bell-shaped error, that means that if this X is a bell-shaped, okay, and turn out to be your intercept is also like a bell shape. Okay, so the intercept will be centered at this A, but it's a bell shape along it. Okay, same as intercept. Okay, same as the slope. Okay, so everything will become normal. Okay, if you are willing to assume, make this assumption, then you're the bell. Okay, and easily everything would follow to say you just minus 0 over the standard error, okay, then you have t-test, okay? And similarly, B, you also assume a bell, you also have B will be followed by bell as well. And you can also do a t-test. You can do a interval estimate, okay? And the next we will do is ANOVA. And ANOVA again turned out to be similar idea. And in this particular case, okay, ANOVA related to what we call R square, okay, is later we'll explain is how good is this linear model. Okay, we're not going to go into detail on this. We'll talk about next class. Okay, and afterward, as we see, ANOVA, okay, when we say there's a two group in one way ANOVA is t-test. Okay, so here we'll prove some idea here because we only have one variable, and when we do ANOVA here, it's exactly same as a t-test. Okay, turn out to be if you do the t-test on beta, it's same as ANOVA. Okay. Finally, we want to do a interval estimate on the prediction. Okay, why? Okay, so what does that mean here is very simple. Is suppose I have a line here, right? Use this line. Okay, then I have this particular x0. I go up here. Okay, what is the interval estimation of this y, right? Because the bell shape is here, right? So this is a point estimate, and I want an interval estimation. Okay, so that will be the end goal of the whole class. Okay, so I will see you next week. Then probably next week we are almost done. Okay, then enjoy the weekend. Thank you.